Okay, so now we can state a much stronger result. Let the set B be a non-empty set. Then the following are equivalent. If we say that the set B is countable, this is equivalent to stating that there exists a surjection mapping the positive integers onto the set B, and this in turn is equivalent to the condition that there exists an injection mapping the set B into the set of positive integers. So notice that if there exists a surjection mapping the positive integers onto the set B, then the set B has at most the same number of elements as the set of positive integers. And if there exists an injection mapping the set B into the set of positive integers, then the set B has at most the same number of elements as the set of positive integers. So proof. We'll show first that the first statement implies the second. So suppose that the set B is countable, then the set B is either countably infinite or finite. Now, if the set B is countably infinite, then there exists a bijection, which we'll call F, mapping the set B into the set of positive integers. And so the inverse function F inverse exists, and this is a map from the set of positive integers into the set B, and this is also a bijection. So as it is a bijection, it is certainly a surjection. Now if the set B is finite, then there exists a bijection which we'll call G, mapping the set B into a terminating subset of positive integers, consecutive positive integers beginning with 1 and ending with n for some positive integer n, where that integer is greater than or equal to 1, since the set B is not empty. And so the inverse of this function exists, and it is a map from a terminating subset of positive integers, consecutive positive integers from 1 to n, into the set B, and this is also a bijection. Now we can extend the map G inverse into a surjection, which we'll call H, from the set of positive integers onto the set B, defined by h of I is the same as G inverse of the element I, where I ranges from and including 1 to and including n, and G inverse of the element 1 for all elements I greater than n. That is, the map H is identical to the bijective function G inverse for all values of the element I ranging from 1 and including 1 to n and including n, and for all other values is mapped onto the same element, so this is a surjection. So in either case, if the set B is countable, then there exists a surjection mapping the set of positive integers onto the set B. So next we'll prove that the second statement implies the third. So let the function f from the set of positive integers into the set B be a surjection then define a function g mapping the set B into the set of positive integers by g of B is the smallest element in the fiber of the element B. Now, as the function f is a surjection for every element B in the set B, the fiber of that element is not empty. And so the function g is a function from the set B into the set of positive integers. Now if the element B is not equal to the element B prime, then the fibers of these elements are disjoint and so the smallest element in the fiber of the element B is not equal to the smallest element in the fiber of the element B prime. That is, G of B is not equal to G of B prime, and so the function G is, which is a map, set B into the set of positive integers, is an injection. Okay, so next we will prove that the third statement implies the first. So let the function g, which is a map from the set B into the set of positive integers, be an injection. Notice that the function g prime, mapping the set B into the range of g, defined by g prime of B is equal to g of B, is a bijection where the range of G is a subset of the set of positive integers. So if the range of G is finite, then the set B is finite, and if the range of G is infinite, then since the range of G is an infinite subset of the set of positive integers, it is countably infinite, and so there exists a bijection, H, mapping the range of G into the set of positive integers. Where this function H is a bijection. And hence the composition H of G prime, which is a map from the set B into the set of positive integers, is also a bijection. And thus the set B is countably infinite. So in either case, if there exists a surjection, an injection, mapping the set B into the set of positive integers, then the set B is countable. So this theorem has an immediate corollary. Subsets of countable sets are countable. So proof. Let the set B be countable, and let the set A be a subset of the set B. Then, as the set B is countable, there exists a bijection, which we'll call F, mapping the set B into the set of positive integers. And so the restriction of the function f to the set A is a map from the set A into the set of positive integers, and this is an injection. And hence, by the previous theorem, the set A is countable. Okay, so this corollary itself has an immediate corollary. Arbitrary intersections of countable sets are countable. So proof. the collection C sub I for I in some indexing set I be an indexed family of countable sets then the arbitrary intersection of these sets is the subset of the set C sub I for every index I, where each of these sets is a countable set, and hence the arbitrary intersection of countable sets is countable by the previous corollary. So next we'll establish a lemma. The set, which is the Cartesian product of the set of positive integers with itself, is countably infinite. So proof. Define a function f from the Cartesian product of the positive integers into the set of positive integers by f of the ordered pair mn is 2 to the power of m times 3 to the power of n. Suppose that the function taking as an argument the ordered pair mn is the same as the function taking as an argument the ordered pair pq. Then 2 to the power of m times 3 to the power of n is equal to 2 to the power of p times 3 to the power of q. So let's assume that m is not equal to p. Then in this case, we're dealing with two integers, m and p, so one must be greater than the other. So without loss of generality, we may further assume that m is less than p. And so we have that 3 to the power of n is 2 to the power of p minus m times 3 to the power of q, where p minus m is greater than or equal to 0. Correction, is greater than 0. But this says that a power of 3 is not odd, rather it is an even multiple of some other power of 3. So this contradicts that 3 to the power of n is odd for every positive integer n, and hence by contradiction we must have that m is equal to p. And so we have 2 to the power of m times 3 to the power of n is equal to 2 to the power of p times 3 to the power of q. As m and n, as m and p are equal, we can cancel out those factors so that we have 3 to the power of n is equal to 3 to the power of q, and hence n is equal to q. That is, the ordered pair mn is equal to the ordered pair pq, and hence the function f is injective, and therefore the Cartesian product of the set of positive integers with itself is countably, or is countable by the previous theorem. And as this product is not finite, it is countably infinite.